So we will solve now problem 10. Consider a viscous film of liquid draining uniformly down the side of a vertical rod of radius small a, as shown in the figure. At some distance down the rod, the film will approach a terminal or fully developed flow of constant outer radius b, characterized by Vz only function of r, and V theta and Vr equals to 0. Assume that the atmosphere offers no shear resistance to the film motion. Derive a differential equation for Vz and state the proper boundary conditions and solve for the film velocity distribution. Okay, so first, what we want to do is to find the velocity flow, the variation of flow profile. And after this, we will find how does the film radius B relate to the total flow rate Q. So once we find the velocity profile, we can calculate the volumetric flow rate Q. So first here we are working in cylindrical coordinates. So we will apply the Navier-Stokes in cylindrical, not rectangular coordinates. Okay. Now let us see the given and how to use them. So first we have, they gave us that V is only function of R, okay? And V theta and Vr equals to 0. So V is moving along Z, but it's function of R. And as you can see here, Z is the vertical direction. It's going down. And here, if you want, the flow is over a cylindrical part. So we have a film of oil moving over a cylinder. So here, if you want, you have, this is A, the radius of the cylinder. So you can say that you can apply the no slip condition at this surface. Okay. So at this level, you have the velocity of the wall is 0. Okay. So you can apply the condition that velocity at this level is 0. So for R equal to A, for R equals to A, I have that V of Z is 0. Okay. And what is the second condition we use? They said assume that the atmosphere offers no shear resistance. What do we mean by no shear resistance? What can we conclude?
maximum velocity على هونيك.
Okay, maximum velocity هونيك بس نحكي بشير يعني we talk about the gradient of velocity. Okay?
Yes.
يعني del U. So at what we can say at R equal B, since no shear resistance, then del V by del Z, del V by not by del Z, by del R, okay? Because here the variation of V is with R, not with Z. Del V by del R is equal to 0 at R equal V, okay? So these are the boundary conditions we will use. Now we should find the differential equation, okay? So to get first the differential equation, we need to go back to the Navier-Stokes equations, but apply them now in polar coordinates. Okay, and we will apply in which direction here? In which direction we will apply Navier-Stokes equation?
Positive Z, downwards.
Yes, because the flow is moving in Z, so we will apply the Navier-Stokes equation in Z. Okay, so let me go to our equations. It's here. So let us go to the equation along Z, this one, and we start to simplify the terms. First, it says it's a steady state application, so this term is 0. We said that Vr and V theta are 0, so this is 0, this is 0, and this term will be 0. Why? Because they said Vz only function of R. Okay, so to justify, this is steady. Okay, Vr is given to be 0 V theta is given to be 0, and since Vz is only function of R, so when we derive Vz by del Vz by del Z, it will give us 0. Okay, so from this side we don't have any term. Now from the other side, what do we have? We have minus del P by del Z. We have plus rho Gz. Okay, now if you want, since your flow is already moving down, you can take, so you know that your velocity is moving down, so you can take y-axis downward. Okay, so if you take your y-axis or z-axis, sorry, if you take your z-axis downward, what will be Gz?
G.
It will be plus G, not minus. Okay, so here you can take Z downward, and Gz is so Gz is equal to G. So we can replace this term here. This term can be replaced by rho G. Okay, now from the other side we have we said that Vz is a function of R, so this term will not be 0 because del Vz by del R is not 0. Okay, now for the other terms, del Vz by del theta second derivative and second derivative of Vz with respect to Z are 0 because Vz is only function of R. So these two terms can cancel out since Vz only function of R. So Vz is only function of R. Okay, so our equation reduced to what? To minus del P by del Z plus rho G plus mu times 1 over R del by del R del Vz by del R. Okay, now what about this term? What about del P by del Z? Look, let us go back to the problem to see the figure. Okay, if you look at the figure, they said that the pressure at this level is equal to the atmospheric pressure. So P is not varying in a Z direction here. Okay, so we can conclude that del P by del Z is 0. Okay, so since P equals to PA is not varying with Z, so del P by del Z is equal to 0. Okay, so this term will cancel out. Now
Where did they say this?
look, it's written here. You have PA at the atmospherical level. They put PA, so constant pressure, and we neglect the shear because they said that viscous. So here they said shear resistance
1R equal to B.
neglected, and here we have that PA, and they said also that it's exposed to the atmosphere. Okay, so the fluid flow is exposed to atmosphere, and we neglect variation of pressure for atmosphere because you know that for air the density is very small, so the change in altitude will not affect a lot the pressure. Okay, clear?
Yes, doctor.
Okay, so now when we simplify del P by del Z, we still only have the two other terms. Okay, rho G and 1 over R d by dr R dVz by dr. Okay, so if we replace here, if we take rho G to the other side, we get that 1 over R d by dr R dVz by dr equals to minus rho G over mu. So now to be able to get the profile Vz, we need to integrate this relation 2 times. So let us do it here. So first, what I will do to be able to integrate the first time, I will take R to this side. Okay, so I will multiply this term here by R. So I get the following. I get d by dr of the function R dv by dr is equal to minus R times rho G over mu. Okay. Now, if we integrate this relation for the first time, يعني d by dr here بتروح due to the integration. So يبقى عندنا the function r times dv z over dr. Let us put z here. Okay, equals to, if we integrate here from the other side with respect to r, it's minus r square over 2. Okay, so you have minus r square over 2 times, هلا إذا بدكم let us put 2 at the end. So minus r square times rho g over 2 mu. Okay, over 2 mu. This is the first integration. Now, before doing the second integration, the r that is here, we will take it to the other side. So we will divide the whole equation by r. So if I divide the whole equation by r, divide by r, I get that dvz by dr is equal to minus r times rho times g over 2 mu. Okay, and now I can integrate now I integrate a second time, so with respect to r, so I get the integration of this term will give me vz equals to, from the other side I have, what we forgot to do, what here we forgot to add a constant, so please don't forget the constant, plus c1, and when we divide by r we get plus c1 over r. Okay, now we integrate this relation, so it will give us, for the first term, when we do the integration, it's the integration of r is r square over 2, so we get minus r square times rho g over 4 mu. Now, integral of 1 over r is ln r, so plus c1 times ln of r, and we don't forget to add the constant c2, so plus c2. Okay, so this is our vz. Now, the final step is to get c1 and c2. To get c1 and c2, we need to apply boundary conditions. Okay, and boundary conditions, as we said, if we go back to our figure, we have two boundary conditions at r equal a, v equal 0, and at r equal b, del v by del r equals to 0. Okay, so first, so these are our equations. Okay, for del v by del r, we have the conditions that for r equal b, for r equals to b, dv by dr, dvz by dr is equal to 0. So if I replace in this relation, we get that for this condition, minus b times rho g over 2 mu, and plus c1 over b plus c1 over b equals to 0. Okay, so we did use that, so c1 is equal to minus b square times rho g over
دكتور plus مش minus plus.
yes, plus, sorry, because we take it to the other side. So plus b square times rho g over 2. Okay, so this is the value of c1. Now, to get c2, we apply the second condition. The second condition is that we have for r equal to a. Okay, so here, if you go back to the figure, for r equal to a, what is the condition? The velocity is equal to 0. Okay, so for r equals to a, vz equal to 0, vz.
For r equal a, use 0.
Yes, for r equal a. For r equal a, we have that V is equal to 0. So Vz of A is equal to 0. Okay, so if we replace in the equation, we have that 0 here, replace here, 0 equals to minus A square times rho times G over 4 mu plus C1. You can replace C1 by its value, or you can replace it at the end, okay? So plus C1 times ln of A plus C2, okay? So we conclude, so C2 is equal to plus A square times rho G over 4 mu and minus C1, and if we replace C1 by its value, so minus B squared times we have 2 times rho G over 2 mu, okay, and times ln A and that's it, okay. So we got the expression of C2, function of our variables. So now all we have to do is to plug in into our equation. If you plug into your equation, you can simplify terms. How you can do it? By taking some terms into factor, okay? So for example, if you take rho GB squared over 2 mu, you have it's times ln R minus ln A, and ln R minus ln A is ln R over A. And you can take also another term into factor, which is rho G over 4 mu. So if you take rho G over 4 mu, you get into factor A squared minus R squared, okay? Do you want me to replace in detail, or it's fine? If you want, we can do it step by step to get this relation.
It's fine.
Okay. So we will solve في problem we didn't solve it. Let us solve it now. على ال
دكتور
continuous.
فينا
Yes.
هلا هي لما يقولوا لنا assume the atmospheric أو the atmosphere offers no
Yes.
shear resistance دغري
Yeah.
بنفهم منها إنه دي في زد over دي
Yes.
دي
Because
ار
the
equal
shear is
لزيرو.
proportional to the
لأنه
distance.
يونيفورم، يعني كأنه يونيفورم الفيلوسيتي.
مش يونيفورم، انه صارت يعني من هلا ورايح صارت يونيفورم. Yeah.
Yes.
Yeah. Okay. Just بعد ما خلصنا في one additional question here. They said also to calculate the flow rate. Okay. So now we want to compute the flow rate Q. Who will tell me how to calculate Q here? So also here we have a velocity profile. We have a varying velocity. It's not constant. So
U
also,
times dA?
yes, exactly. So here also we need to integrate. But here we should choose the dA in a good way. So here to find the Q is integral V time integral of Vz dA. How you will choose your area here, your elementary area? How to choose
تطلع
it?
2 pi r into b minus a.
2 pi r into what?
ناخد b minus a.
No, look. إذا بتعمل هيك you are not you are finding the total area, بس حتى the total area مالنا 2 pi r b minus a. Look, this
Pi
is
b squared minus pi a squared.
بس أنا I don't want the total area. I want to take an elementary area. Look, if you look from the top, this is your cross section. Yes or not? So you have this form. This is your cross sectional area. But when you do the analysis to take dA, you should choose an area for which the velocity is not varying. Your velocity is varying with what? With which direction? Your velocity is varying in R. Okay? So when you choose your elementary area, you should choose it in a way to have no variation of velocity. So it should be a thin disk. Okay? It should be a thin disk. So you would choose it like this. If I consider here a thin disk, okay, of thickness what? I will take a thickness dr. So I will take a thickness dr, and So if this is dr and we have the radius here is r, so I can say that my elementary area is what? It's 2 pi r dr, because here I will take a very thin disk of thickness dr and of perimeter 2 pi r. So this is, I will draw it here if you want. So it's not very clear. I will draw it here above. Okay, so you take ما عم تزبط 100% الفيجر. اوكي بس انه you take a thickness, a very small thickness dr and the perimeter is 2 pi r. Okay, why we take this area? Because we can say that everywhere in this area we have the same velocity. Okay, and then we integrate over the whole area to get the total flow rate. So we will choose dA as following. dA is equal to 2 pi r dr. Okay, then we can consider that for all elements of this area, what is the velocity? The velocity is, so for all points of this area, for all points of this area, the velocity is vr. Okay, so now if I want to find the q, okay, then q is simply, I will integrate from which location to which one. R is varying between what and what? Look, your flow starts here and it ends here.
Between
So,
A and B.
yes,
A
so
to
the radius
B.
is varying between A and B. So q will be equal to integral from A to B of Vz, which is a function of R. So I just replace Vz by its function times 2 pi r, so times dA, which is 2 pi r dr. Okay, let us see together the solution. So I have just to replace my function. Okay, so this is my function and I will integrate it between A and B. Okay, so and I should multiply it by 2 pi r dr. هلا the function is little bit complex, but you can if you want, يعني نحن بنعطيكم simple integrations. We will not give you complex integration, so don't worry about this. All I want from you is to know to reach this step. So once you reach this step, it's fine. Okay, and the function given will be easy to integrate in the exam.
دكتور نحن هون كان عندنا سلندر قاعد بقلب سلندر
Yes.
في
Yes.
اويل فيلم بده يقطع بقلبه. اوكي
مظبوط. اوكي.
Thank you, doctor.
بس الفرق تقول لك شو الفرق هون؟ ليش مش اذا في سلندر بقلب سلندر بيكون عندك الكونديشن على الباوندري اثنيناتهم نو سليب كونديشن، بينما هون لانه عندك it's exposed to the atmosphere from the other side you have the boundary condition of zero shear. يعني لو كان سلندر بقلب سلندر كانت بتفرق الباوندري كونديشن وبتفرق الايكويشن.
يعني كأنه عندك سلندر وعم تصب عليه فوق من فوق مي.
مظبوط. Exactly.
Okay. Thank
Okay.
you, doctor.
Because we still have time, I will solve problem ما تركناه وقتها عن ال continuity. Problem 5. Okay. So we have that an incompressible flow in polar coordinates is given by Vr equal to k cosine theta times 1 minus b over r squared, and v theta equals to minus k sine theta times 1 plus b over r squared. Does this field satisfy continuity? And second, for consistency, what should be the dimensions of k and v? And finally, sketch the surfaces when Vr equals to 0. So first, to verify that it's satisfying continuity, since it's a steady flow, so I will go to polar coordinates and look at the condition of continuity in steady states. So if I go to my review sheet, okay, Let us go to continuity equation in polar coordinates. It's here. Now, I have a steady application, so this term is 0. And I have a 2D flow, so I only have VR and V theta, no VZ. So no VZ because 2D flow. Okay. And no, here, no del rho by del T, because we can have here two possibilities, or steady or incompressible. Okay, so it depends on the given. So this is our equation. So to satisfy continuity, I should satisfy this condition. 1 over R del R rho VR by del R plus 1 over R del rho V theta by del theta should be 0. So let us verify that this is applicable in our problem. So let's go back to our equation given. They gave us VR function of R and theta and V theta function of R and theta. So now we replace in this equation to make sure it will give me 0. So first, if you multiply VR by R, what do you get? So R VR from here I have that R times VR is equal to K cosine of theta times R minus B over R. Okay. Now, if you derive this relation with respect to R, what do you get? You get K cosine theta, okay, minus, if you derive minus B over R, you get B over R squared, okay? So if we replace into our equation, we have that instead of RVR, the del of del R with respect to, so let us do it here. If we derive this term, okay? If you derive this term with respect to R, what do you get? You have K cosine theta R. This is your function. K cosine theta R minus times, if you want, K cosine theta times R minus B over R. Okay? If you divide this relation, you can, since you are deriving with respect to R, you consider that K cosine theta is a constant. So it will give you K cosine theta times the derivative of R is 1. And if I have 1 over R, what is the derivative? It is minus 1 over R squared. And already I have minus, so plus B over R squared. Okay? So if this will be my term, K cosine theta times 1 plus B over R squared. Now, for the second term here, if I derive V theta by theta, if I derive this term with respect to theta, I have that the derivative of sine theta with respect to theta is cosine theta. So this term here, if I derive it, I will replace by minus K cosine theta minus K cosine theta times 1 plus B over R squared. So I treat R as a constant when I derive with respect to theta. So as you can see here, these two terms will cancel out. So here I have 1 over R times K cosine theta 1 plus B R squared. And from the other side, I have minus 1 over R K cosine theta 1 plus B over R squared. So the two terms will cancel each other. Okay? So now, this is the first question. I verified that it is satisfying continuity. Now, what should be dimensions of K and B? You remember the dimensional analysis? First, for B, look, you have 1 minus B squared over R. The 1 is without unit. So to be consistent, B also should be without unit. So what should be the unit of B? R is in meter and it's R square, so B should be in meter square. So the dimension for B is L square. Okay. Now for K should be of the same dimension of what?
Meter per second, yeah.
Of velocity, because here V from this side you have the unit L over T. And from the other side also you should have L over T. Now cosine theta times 1 minus BR squared, this is without dimension. Okay, so K should have the same dimension of V to have consistency of units. So the unit of K should be L over T. Okay, and the final question is to sketch the surface where VR is 0. The surface is corresponding to VR equal to 0. This is the expression of VR. If I put it equal to 0, what this can be obtained for what? I have two possibilities, or cosine theta equal to 0. This is the first possibility.
أو 1 minus B على R squared equal to 0.
Yes, or 1 minus B على R square equals to 0. So the first equation, cosine theta equals 0, will give me that theta is equal to 90 degrees. And the second condition will give me that R is equal to radical B. So if I want to sketch these conditions in polar coordinates, first, what is theta in polar coordinates? It is the angle between the position vector and the horizontal. Okay? So when you obtain theta equal 90, this means what? That you are moving on a straight line, which is doing with the horizontal an angle of 90 degrees, which is the y-axis. Okay? So the first line corresponding to VR equals 0 is the y-axis, which corresponds to theta equal 90. To theta equals to 90 degrees. And the second condition is the surface for which VR is 0. Its equation is R equal radical B. So R is constant. If I have constant R, this means what? In polar coordinates, this means that I'm moving along in 2D, I'm moving along a circle. Okay, so since R is constant, then the second surface is a circle of radius radical B. Okay, any question on this? Or any question on problems of this chapter? So we are done with chapter 6. Okay, chapter 7 is one of the easiest chapters. So please, for Wednesday, try to cover, as I told you, until slide 13. Okay, and we can finish chapter 7 this week. So you will have, if you want, next week we can do a review. Okay, so see you next time. Bye.
Thank you, doctor.